All right, welcome back to 353. All right, there's only a few people that want to actually do well in this lab. So this lab, in order to get you up and starting and at least looking at quickly, there's like 5% of this lab is something you have to submit a week from now. It's just like an early test. It will take you all of 5 minutes if you want it to. So go ahead and do that. Otherwise, we are doing user threads. So we're going to do cooperative user threads in this, and I will show you the functions that will do the heavy lifting, because essentially we are implementing our own threads, and remember, threads are basically just registers and a stack. So I will show you the library function we can use that will do all the heavy lifting for us for swapping in and out registers and saving them and all that good stuff. And I will also allocate you a stack. And this will be also the first lab where you will have to use linked lists. So because this is the first lab where you'll have to use linked lists, I will show you a library for linked lists first, because you shouldn't ever have to write your own. So for this, you can access all of these examples. They're in that materials repository. I actually pushed it. So you can use this as a basis to go ahead and start your lab. So for the first one, I will run through it really quick. Instead of implementing your own linked list, guess what? They are already written for you. You don't have to do that. So with this, we're doing cooperative user threads. We're going to have to do some first in, first out scheduling, which necessitates probably a queue, which it would be nice to have a doubly linked list because, well, we probably want to get a thread from the front to run, and then if we create a new one, it goes on the back. So probably want a doubly linked list, and no one should ever have to write their own doubly linked list, even though everyone seems to love doing that. So there is this library called the queue library, and inside of it are a bunch of macros for a bunch of functions that will go ahead and write these things for us. So a doubly linked list in this library is called a tail queue. Don't ask me why. And it's basically a whole bunch of macros. So tail queue head means I want to define essentially a list, and I will give it this name. So it will create a struct called list head, and that will represent our list. So like this, it would be the structure that has like a pointer to the first and the last element of our list. And then also we tell it what the structure is of each element we are going to hold in this list. So in this case, I called it list entry. Up here, I define struct list entry. So all I'm going to do is have an ID. So my fields are just going to have a single ID. If you want to add more to it, you can, but for this lab, you should only need like a linked list of thread IDs and what order to run them in. And then there's this tail queue entry, so you just give it the name of the struct, and then the name, just some unique name that you use later, and that will go ahead and define, in this case, like a next and a previous pointer for you. You don't have to do that. And the nice thing about it is if you, for some reason, want to make this a singly linked list, all you have to do is change the macro name from tail queue to, I think it's slist, and boom, it's a singly linked list. You don't have to do anything different. So this defines the pointers for us. This defines a structure called list head. So we're only going to create one list. So we'll create a global variable called list head. Just call it list head. And then we'll scroll down to main. So how we actually use it, we have to call init to initialize it. Oops. So we have to call init to initialize it. We give it the address. There's this empty function, so we can ask yes or no, is the list empty? Well, because we just initialized it, we haven't added anything to it. It should be empty. And then I'll just create a list entry on the stack. You probably can't do this. You probably have to malloc your entries. But in this case, I create one on the stack. I give it the ID 1. And then I do insert tail. So there's insert tail to put it at the back of the list. There's also an insert head macro if you want, and you just give it the address of the list the address of the entry you want to add, and then the name of your pointers field that should exactly match whatever you used for the entry function above here. So you do that, goes ahead, and then it inserts 1 into the list. Yay, we don't have to write our own list. And then here, if I print list, so in print list, all I do is print list, and then declare a pointer to a list entry, and then there's this tail queue for each that will go ahead and iterate over every single element of the list for you. No dealing with next and next pointers or previous if you're going backwards, anything like that. You give it the pointer you want it to set, the address of the list itself, and then again the name of that pointers field for the entry. And here, well, we only have an ID, so we can print off the ID, and that's it. So after that, we create a new entry, ID2. We can insert it to the end, so we can print off we inserted it, print off the list again. Now it should be 1, 2, and then we can print list last. So there's other functions. If I just want to get the last element, I can use tail queue last. There's tail queue first if you want to get the first one. So we can go ahead and just wants the address of the list, and then just the name of the structure, and then that's all we do, and we can get the last element. And then if we want to remove it, we can go ahead and remove it using tail queue remove. We just give it the address of the entry to remove. That's it. No playing with pointers. Isn't this much easier than implementing your own list? I suggest you do this. So if I go ahead and run this, should be not very exciting. So I inserted 1. There's a 1 in my list. I inserted 2. My list has 1 and 2. The last element is 2. If I remove 1, my list just has 2 in it. Questions about that? Yeah. Sorry? So the pointers is just the name of the entry here. And this will essentially, in this case, that'll be like the name or like the namespace of like the next and the previous pointer. So it's just how it works. It's C, so it just does hacky stuff with macros. But it works. You don't have to implement your own linked list. All right, good for linked list. Highly recommended to use this one. All right, let's go to the hard part. So there is this thing called a ucontext. So ucontext is a library function you are going to use that will do all the heavy lifting of saving registers, swapping registers in, and all of that fun stuff. So you can think of ucontext as just a copy of all the current registers. So there's 4 ucontext functions we're going to use, and the first one is getContext. So what getContext does is it just takes an address of a ucontext, and it will save the current state of the thread, like all of the thread's registers, to that structure so we can go ahead and restore them later. So that would save literally everything, the stack pointer, the instruction pointer, every single register, and what their value currently is. So so all this does, it initializes this ucontext that we just called thread 0 ucontext. So if we go up here, I just declared 3 global variables. I just declared 3 ucontexts. So we're going to essentially create 3 threads in this program. So we're going to call thread 0. We're just going to give thread 0 the name of the main thread. So we'll just assume that it's main 0 or thread 0. So if I do get context here, it just saves the state of the current thread that is executing it. So like I said, literally everything. So questions about that? So it saves all the registers and everything to that. Okay, so we can ignore the comments for now. The fun thing is that is the save, and then setContext is essentially to restore all the registers. So if I do something like that, if I do setContext, what it will do is it will read all of the registers that are in this context structure and just restore them all to whatever they were saved at previously. So if I do this, if I set context, what's going to happen is, well, I saved them last up here at this line, including the program counter and everything like that. And if I set context, what it will do is it will restore it. So my code will go back up here, and it will look like it's just coming back from get context. So if I do this, and I run it, I do something like this, what's going to happen is I'm going to have a fun infinite loop. So it's just going to have an infinite loop here. Because what's happening is I get context, I save all the registers to this thread 0 ucontext, then I print f hi, and then I set context, which means I restore it back to the last place I saved it. So it goes right back to get context, we print off hi, and then we restore it, go back to get context, print hi, restore it, go back to get context, print hi. We have infinitely looped ourselves immediately. So questions about that? Yeah?
How do you progress from that thing?
How do I what?
How do you progress past set context?
So how do I progress past set context? We probably want to switch back to something else and then maybe resume and not do this. So we probably want to avoid this at all costs. So yeah, next question is how do I make it be more useful than this? All right, so we'll get to that in a second, but any questions about why this is an infinite loop? Does everyone understand why this is an infinite loop that just keeps going on and on and on and on and on again? You may encounter this if you actually do that, because essentially for your threads, this is going to be all your registers, so you are managing this thing. So that clearly a bad idea. All right, so in order to make it useful, well, if we just like kind of rewind a thread back in time, doesn't seem that useful. If we have threads, we're doing concurrency, right? We're switching back and forth between them. So we at least need one other thread. So there are some other functions I gave you. So there is a function called new stack. What that will do is allocate a stack for you. So you just call new stack, you get a pointer back for your new stack. And you can go ahead and use it. So if we want to create a new thread, well, each thread needs its own stack. So I declare a new stack for, I'll call it thread 1. And then we need a ucontext to represent the thread's registers. So we just need two things to represent a thread and registers. So after this step, we have both. Oh, we have a good question. All right, so if malloc was incremented between set and get context, would the variable increase? A malloc variable. Yes. So if I did something like whatever, I'll shortcut it. Yeah, so, whoops, wrong. Compile. So, whoops. I need to infinite loop myself again, sorry. So, yay, it increases. Because, well, it's on the heap, doesn't really matter. So if I malloc it, between this, I'm just incrementing that memory location over and over and over again. So it would go ahead and grow over and over and over again. So yeah, you would get into trouble with that. All right. So let's go back to creating a new thread. So we're going to create thread 1. Like I said, we need a stack and then registers. So in order to initialize the uContext for thread 1, we just have to use get context even though we're not planning on resuming this at all. It's just used to initialize something, so we always have to use it. So we do get context and save the current registers, which is like the main thread, to thread 1 ucontext, but we're going to overwrite it shortly. You just have to initialize it with this. Don't ask me why. And then in the ucontext, there are some fields we can do that will go ahead and tell that ucontext that I don't want to use the stack that I currently saved. I want to use a different stack. So you can set its stack pointer to the stack we got back from the new stack call, and then you also have to say what the size of the stack is. In this case, new stack gives you a new stack that is this size back, 16 kilobytes. Don't really worry about it too much. It's just this macro. So that is the size of our stack that we will be using for this code. Now, in order after that to actually have this function go ahead and update all of the registers, we can use make context. So make context takes as the first argument the address of the ucontext to use that should be already initialized with get context that we're going to go ahead and change some values of. So we change this so it would go ahead and find the register for like the stack pointer and go ahead and update it to actually point to the stack that we allocated for it. And in addition, it will change the program counter for us to actually start running this function we give it. So the second argument is a function, and it will initialize the program counter so that if we do a set context to thread 1 ucontext now, we will start running this function called thread 1 run. And the function just takes no arguments and returns nothing, but it turns out you can actually optionally give it some arguments, which you may or may not want to do for your lab. There's different ways to implement it. So if you want to give it arguments, the next argument to this function is argc. So that's how many arguments you're going to pass to that function, and you can only pass integers to it. So here, I'll just pass one integer to it, and then just give it the value 42, and this is the argument we can pass. We can only pass integers. So in my thread 1 run, there's one integer argument. I can say, hooray, if I'm actually executing this, I'll say, hooray, I got arg0, print off the value, and then I'd be done with this thread, kind of like p threads. So, any questions about that? So, what I can do is, well, after I make context, I'm currently running the main thread, but I can just immediately do this. I can set context to that, and what that should do is immediately just swap the current registers with whatever I saved in thread 1 ucontext, which should use thread 1's stack, and then start executing this function. And then it should say, hooray, I got arg0, whatever that would be. So if I run that, I get, yay, I did it. Hooray, I got arg0. So questions about that? So I just changed what thread I have now. So I created a new thread, called it thread 1, gave it a new stack, told it to run this function. So kind of looks like p threads, right? Except, guess what? They're user threads. The kernel has no idea what the hell we're doing. We're just kind of playing with stuff ourselves. So, other rules are with ucontext, if it actually just reaches like the end of this function, well, guess what? It just exits the process. Process is done, nothing we can do. So in order to make sure that I don't just exit the process, well, maybe I'd be like, okay, well, now I know thread 1 is done, so I shouldn't run it anymore, but there's something else I should run. So what would happen if I did something like this? Or it's like, oh yeah, I could just go back to thread 0. There, I can move that out of the way. Something like that. Yeah. Sorry? Do the same. Yeah, kind of. It kind of looks like I do an infinite loop again. Wait, was that? Yeah, so if I do this, essentially I just create a bigger infinite loop. So I do this, I run it, I get hooray, got 42 over and over and over again. Why? Well, what happened here is I saved the current registers to thread 0 ucontext as the first thing I did in main. Then I created a new stack. Then I initialized thread 1 ucontext. I set it stack, and then I did this make context, which went ahead, set the program counter, set the stack pointer registers, and set everything up so it would start executing that function. I did a set context to the thread 1 I just set up. So I immediately start executing this function with thread 1 stack. And then at the end, I do set context to thread 0. So that will go back and restore whatever was saved in to thread 0. And whatever was saved into thread 0 was last done at the beginning of main. So it would come back here. And then thread 0 would go ahead, create a new stack again, set up thread 1 again, and then switch to thread 1. Thread 1 would run, then switch back to thread 0. Da, 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 and this keeps on going infinitely. Yeah?
I'm a little bit confused about what these different functions are doing. So is set context the thing that runs the function that you've saved?
No, set context just restores all the registers in that ucontext.
Okay. What does make context do?
So make context will essentially initialize the registers so it changes the stack pointer to start running that function that you gave it.
Okay. So make context is sort of like the pthread create that we had before. You have to get context before you do that.
Yeah. So make context is, you can see it's kind of like pthread create.
And get context is like save the current area that you're on in the file. Like save your current.
Save where you currently are, and then that way if you do a set context back to it, it looks like you just returned from get context.
Does it continue executing from the line that you get context on? How does that work?
Yeah, it looks like it just continues executing after the get context call.
So that's why when you get an infinite loop if you have a get context, set context, because it
Yep.
executes.
Yeah, so that's why we got an infinite loop, because here if we get context, so we save it, and then set context restores it, so it looks like it just starts executing here. And then next line is set context, so we go back there, set context, go back, set context, go back.
So when we use get context, is it essentially like, so what we want to do here is we want to execute some thread, and then when we want to do a swap, I don't remember what it was called.
Context switch.
Context switch. We would get context on the thread that's currently running, and then make context or set context on the other thread that we want to execute.
Yeah, sounds good, but there's some difficulty there. Because, yeah, what he's saying is, well, if I want to switch to another thread, well, I should probably like save where it currently is, and then set context to a new thread, and then when it's done, it should set context back to me. But you have a little bit of a catch-22 situation there, right? So if I did get context, so let's just say I went ahead and I save this.
Oh, because it would execute the next set again once you come back.
Yeah. So if I do this, this like has the right idea, right? But I'm saying, okay, I want to like just resume where I was where I was before. and then I'll set context, and then I'll switch to something else. Well, now that something else will go ahead, run, and then set context back to the last get context, which is here, and then it set context, and we just infinite looped ourselves again, right? But except we did it this time, we infinite looped ourselves, but instead of having to recreate the whole thread 0 again, we infinite looped ourselves much more efficiently this time. So we didn't have to go ahead and set up the whole threads again. And yeah, and the other comment was about pthread create. So pthread create kind of does this make context, but pthread create is all of that. So pthread create would need to allocate a new stack and do the make context. There's two things going on, right?
And the allocate a new stack happens in get context?
So the allocate a new stack, it just happened in whatever thread, like my main thread that just created it. Doesn't really matter what creates it. Okay, so yeah, this idea here, so everyone clear why this is also an infinite loop, but more efficient. So what your idea is pretty sound of like how to go back, and that is the fourth function call. So there is actually something called swap context. So what swap context will do is exactly what you wanted it to do. So if I do swap context, and so if I do swap context T0, so if I do swap context is a bit more magical. So what swap context will do is it will go ahead and it will do a get context on this and kind of fudge it so that if you do a set context back to thread 0 context, it resumes right here instead of trying to do the set context again. So it does a little bit of magic. If I wanted to, I could ask you to implement that, but I'm not sadistic. Turns out you can implement it because turns out stacks are unique per, so you can kind of tell whether or not you came back or not, but you might figure that out in a later example. I won't make you write that for this course or for this lab. You can just use swap context. So it essentially does a get context on this, so it'll come back after the swap context and do a set context on this ucontext. But let's go ahead and get rid of that first. So other ways we can, so other things we can do is first, let's just, in order to play with stuff, we'll just create a new thread called thread 2. So I just get a new stack. I have to initialize the ucontext, so I initialize thread 2 ucontext. I set what the initial stack pointer should be, the size of the stack, and then I do a make context, and I give it thread 2 run to run, and then give it no arguments. So now I have 2 ucontext set up that I can use. So if I go ahead and I just do a swap context, what will happen now is I save the context to thread 0. I set it to thread 1. So I should execute this line. And if I just get rid of this, what's going to happen is I just end my process, right? My process just ends immediately. But if I wanted to, what I could do is, well, I could set context all the way back to thread 0. And if I do that, then it will come back here to the swap context, print main is back in town, and then delete thread 2 stack, and that's it. Yeah?
After you delete stack, you need to delete the context?
Yeah, you would probably want to delete the context. In this case, they're all global variables.
I see. So we're gonna let C deal with it.
Yeah, I just have them, they exist for as long as my process exists, because this is a little example. You want to be smarter about that, so you probably need to malloc some stuff. So that's on you, but yeah.
I agree with the exists as long as C exists argument. It's gonna.
Well, in this case, I know I'm only making 2 threads. You don't know how many threads your test case is going to have to create. So if I wanted this to do something more, so first, everyone okay with this? So thread 0, then main initial thread swaps to thread 1. Thread 1 prints yay, and then we set context back to thread 0. So we resume back here, prints main is back in town, deletes thread 2 stack, which we'll see why in a second, and then returns from main, which means we exit the process, which means the process is done, everything's done. Okay, well then, let's do something more fun. So what if I was like, okay, well, after thread 1 is done running, well, if this was like our actual program and we created thread 1 and then thread 2 should probably run after thread 1. So in this case, I can set context to thread 2 ucontext, and then it should print off T2 should be done, switch back to T0. So I can go ahead and now here I might just delete T1 stack because I know I'm never coming back to it. And then I can set context back to thread 0, and then thread 0 will go ahead and print main is back in town, and then delete thread 2 stack, and then everything's nice and cleaned up. I've cleaned up all the stacks I've allocated, and when I run that, this is the message I get from thread 1, this is the message I get from thread 2, and this is the message I get whenever I come back to the main thread. So, are we good with that? Ish? Okay, so other things you could do. So, other things I can do in thread 1. So, if I just delete this line and I run it again, well, thread 0 switches to thread 1. Thread 1 runs this function until it's done, and because I don't switch to another thread or do anything, process ends. So, one way to do this is if I want to run another thread that I already know what it should run ahead of time, which may or may not work for you. You may want a cleanup thread or some thread that you know exists, but in this case, there is another field in this ucontext called uclink, and you set this to a ucontext, and the rule is whenever this run function is done, instead of just ending your process, it will just go ahead and automatically do a set context to this ucontext that you set it. So if I do this, I set uclink equal to thread 2 context. So that means when thread 1 is done running, it will automatically be like it has a set context here to thread 2. But without me having to do that. So you just have to do that before the make context so it can go ahead and set up all of its magic. And if I go ahead and I do that, boom, still works. So thread 1 executes. Because I set uclink whenever it's done, it set context to thread 2. Thread 2 goes ahead. It runs this crap, deletes thread 1 stack, set context back over to thread 0. Thread 0 runs, main and back in town, everything works cool. Right? So any questions? Because this is like most of your lab, except you're just moving stuff in functions and making it a bit nicer. Yeah?
Is there a way to like make the delete all before?
Make what?
The delete stack. Or can you just like save it at the end and delete?
Yeah, so the question is there a way to make delete stack automatic as well? Depends. So you can like, one strategy you might have is maybe like, you know, in pthread, it needs a function to run. So maybe you write like a little wrapper function to run that, finds your real thread function to run. What do I call it? Like start routine. So you set it up so that your run goes ahead and does some of your own setup, calls the start routine that like pthread would want you to do, and then maybe it delete stack, and then maybe it does like an explicit thread exit, because well, the rule of your threads are going to be like if that thread has done its start routine, just like with pthreads, it should implicitly call exit, so you have to implement that. So maybe you think of doing it something like this and writing a different function. You could do this, but if you delete the stack, you cannot delete your own stack if you're still running. That will cause lots of issues. So that is one very, very, very common thing in this lab, is if you try and delete your own stack while you are running, which means you require a stack, you will have a very, 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 very bad time. And you will probably get, at best, you will get a seg fault. At worst, I don't know. You'll be debugging it for a few years. All right, yeah.
I know this was mentioned, but what is the reason of including the delete stack in the thread function? Like technically we can just move it to the main thread, and because we already have like a linked list to keep track of all of the threads, we can just use a for loop and delete.
So you said, what if, so in this case, in my main thread, I could delete all the stacks?
Yeah.
So in this case, maybe, but in general, the main thread might exit before the other ones. Right? So you might have something like, maybe another thread is dead, so you can clean up its stack, but you can't really depend on the main thread to do everything because the main thread might not exist. In this example, the main thread's the last one that exists, but yeah. So in this lab, you'll also be responsible for cleaning up the stack. So every new stack you do should have a delete stack whenever it's done. You're implementing exit, so when you're also implementing a join. So you can clean up you can delete the stack whenever you join on it, for example. It's probably a good time to do it. And then this thread calling join can delete the dead thread stack, and that is fine. You're not deleting your own stack. All right, any other questions with that? Otherwise, we get to do a fun example. All right, so this is a question that was not that. There we go. This is a question that was on one of the exams at one point, and through doing this question, you can probably guess how swap context was actually implemented. So in this case, we're going to assume we have two threads, A and B. They have ucontext all set up. One is going to go ahead and thread A is going to set up and start executing this. Thread B is going to be set up to start executing this line. So I will have two pointers to help me. So, whoops. Oh, that's going to be great. So I will have a pointer for, stop moving. All right. I will have a pointer for ucontext of A to tell me where it's going to resume from, and a pointer for ucontext of B to tell me where it's going to resume. And then otherwise, I will just use a blue to keep track of my variable or where I'm executing. So those aren't global variables. I don't really care about the ucontext, but I have a global variable called I, and same rules apply. It's a global variable. Threads only have their own independent stack, so that's shared between the threads. Within thread A, I declare a variable called D, and I initialize it equal to 0. So currently in this thread, D is equal to 0. Then I have a while loop, so while I is less than 3, currently I is 0, so I go into the loop, and then I change I from 0 to 1. Then I print F. I would print A is 1, and then I set D, and in this case it would be thread A's D equal to 0, and then I do a get context of UA. So I know that if I resume UA, it comes back right here. So then I check if D is currently equal to 0. Currently it is, so it's currently 0. Then I set D equal to 1. And then I do a set context to UB. So I start executing here. So start executing thread B. Thread B has its own stack as well. So in this thread, D is equal to 1. Then I check, is I less than 3? No, I is currently 1. So I would increment I on this line from 1 to 2. Print F, it would print B is equal to 2, or B colon 2. Then I would change D, which is this thread's D, back to 1. Then I do a get context. So if I do a get context, I set UB essentially equal to here. And then I check if D is equal to 1. Oh, currently it is. I set D equal to 0. And then I do a set context here to UA. So I come back and I resume right here. And because I have resumed right here, it would restore the stack pointer. But remember, it's just a stack pointer. The value of D currently on its stack doesn't get reset back. Like we already wrote to it in memory. So D is currently equal to 1. So D does not equal 0. So we would skip over this. So see, we selectively skipped over it. So this is essentially how it would implement that swap context. So we would skip over the set context a second time, right? This is essentially that one-step implemented swap context. So now D is currently still 1, so I would not go into the if statement. I would go back up here to the while. Yeah.
So effectively, the interesting part about this program is the fact that because they each have individual stacks, they don't affect each other and they just keep running.
Yeah, the whole point of this is each thread has its own stack. If you update the value and then you come back to it, the value is still the same. Yeah.
So before, when we were looking at threads shared memory.
So threads do shared memory, which is why they both see the same I. But they have their own stack. Yeah. Sorry? Yeah. So D does not become 1. It was 1 before. Right before we did the set context over to thread B, we set it equal to 1. So when we come back, it's still 1. Because this updates that memory location in thread A's stack, right? And the ucontext just restores the stack pointer. It doesn't reset all the values. Like if I changed 10,000 values, it wouldn't roll them all back, right? It's just a stack pointer, so it moves the stack pointer back so they're in the same spot. Like if I didn't declare D up here, well, if I went ahead and I came back and then I declared a new variable, then it would replay that stack pointer and reallocate it again and probably overwrite what was there. But because I defined it way up there, it was already in scope, it's still the same. Yeah.
So why is it that, so you said this share memory, but they have separate stacks. Why is that I is sort of on this global variable, whereas D is not. How does that work? Are they not both on the stack?
No, I is a global variable. It's in global memory. Anyone can access it.
What does global memory mean? Is that what does that mean?
Global variable, it's just a random virtual address that the compiler picked for you whenever you compiled it.
So that is very distinct from the stack.
Yes, yeah. So
Well, what is the stack?
the stack is what each thread has. So a stack is a data structure, keeps track of all the variables in a function and everything like that.
So any variables that any individual thread declares would be on the stack.
Yeah.
And so, but isn't the int I equals 0, is that not also part of the main thread, or is that?
No, it's a global variable.
Okay.
So it exists, all of them. Technically, these threads, if they knew the addresses of each other's stacks, they could access them. There's nothing preventing that. The only thing giving us sanity is that each thread should only access its own stack, which is what you're actually going to do for that lab as well, because you could try and share stacks between threads. You will never, ever, 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 ever debug that. Just like you won't debug deleting your own stack as you're trying to go ahead and use variables. All right, where were we? Oh yeah, in this case, yeah, so D, still 1. So we'd come back up to the while, check I is 2. We'd increment it from 2 to 3. Our print, we would print A, colon 3. Then we go ahead and we would set D on thread A stack to 0. Get context again, so we'd resume at the same place. Check, oh, D is equal to 0. We set it back to 1. We set context back over to thread B, so we resume right here. Thread B's D is currently equal to 0, so we would skip it here. Go check the while. Is 3 less than 3? No. Okay, we're done. So thread B would reach the end, and because they're ucontext, we can just assume that if it reaches the end, it just ends the whole process. So our final answer would be this. And yeah, this is where, like in the first C programming courses, you might have heard like there's the stack, there's the heap, and there's global variables, and they're all in 3 distinct locations. It didn't matter before. Guess what? Definitely matters now. Otherwise, you're going to be in a world of hurt. So, any questions about this fun example? Because yeah, if I really wanted to, if I did something like, if I had, like say what I said before, if I had like int x here, right after the get context, well, that gets another 4 bytes on the stack, and it would essentially just replay that every single time. So it would probably get 4 bytes, then the stack pointer gets reset before it got the 4 bytes, then it gets the 4 bytes again, Lots of fun. All right, any other questions about threads? We can all implement them now. But yeah, so just remember too that all the code examples I gave today, you can access. So you can do the ye old copy and paste if you would like. But other than that, that's the whole example. Showed you how to make a threads, registers, ucontext, stack, new stack, and delete stack. So good luck and do the early thing. Should only take 5 minutes. So just remember, pulling for you. We're all in this together.